Siemens Step 7, an absolute beginner's guide to PLC programming. Shift register. This is a bonus video for a user that requested some help with a task. As you can see here on the picture, this is the setup that he has. It's a filling station where he fills paste in a tube here. And what he wants to accomplish is that when they scan for the tube to be present and for the product in the tube to be present. This is done by two sensors. One is a sensor that detects if the tube is there, and the other one is a laser that looks into the tube if there is product present. If the product is not present and the tube is present, he wants to discharge it after the band here is like indexing 8 times. There's also an indexing sensor that detects a movement every time it indexes 1 time, meaning that this ejection station is 8 positions after the product detection, meaning that after indexing 8 times, when there is a tube present but not a product present, he wants it to discharge at this position. And he wants to use a shift register that we basically know from microcontroller programming, but it's also possible to do that in PLC programming with the Siemens S7 software, the TIA Portal. I'm using the V15 in order to be able to simulate that because I'm using Windows 10, and with the V14 that he uses, it's not possible to do simulations on Windows 10. So let's dive right in. His requirements were a PLC, a CPU. It's a S7 1200, and it's a 1212C AC/DC relay. And in order to simulate, we have to use version 4 or higher. In this case, we're using version 4.2. And we click on create, and it will take a little while here. There you go, it's created. We also want to go to our properties and switch on the system and clock memory. In this case, we want to enable the use of the system memory byte and enable the use of the clock memory byte. Once that is done, we can dive right into the programming. Go to program blocks, say add new block. In this case, we will call it shift register. We're using LAD, make sure it's a function block. Create. And then we want to start creating our data that we want to use. In this case, we want to create some data in the static area. We need some booleans, and the first one will be let's say index. Then we need a product detection, and we need a tube detection. And then we need some work bits. We make it in an array, just call it work, and then make it a array 0 through, let's say, 9. We should be good with 10. and then of bool. All right, as you can see here, we created a array of 10 bools. That's fine. What else do we need? We need an output for the ejection station. Just let's call it eject, and it will be a Boolean. All right, and then what else do we need? Well, that's it for now. We will create a memory word, but we will do that through define tag. Okay, let's start. What we need first is a couple of networks. You can add by just hitting Control R. So we want to have an index, and we will create that index because we don't have any physical sensors. We will just use the clock memory byte, or at least a bit out of that. Let's see, in order to index, we say clock, and then let's go for something slow so that we can see it here. Clock 0.5 hertz, that means like it will come on every 2 seconds. And then a coil, and let's say this will be index. So every 2 seconds, the index bit will come on, and we will use that later to shift. And then let's go into the instructions, and let's go for shift and rotate, and we will use the shift left, put it in here, and then we will create our memory word. Let's call it just memory word load, and then we have to define this. Define tag, define it as global memory, and define it as a word. Where's word? There's word. Define, and then we want it to shift one position, and we will write that back into W word load. All right. So we want this to happen every time index comes on. We only want to look for the positive edge of that bit here. So we say if index, and then p trig, and let's use work 0. So if that detects the positive edge of index, it will shift the word around 1 bit. So that is also there, and then let's put a network in between those two, because we actually have to load the first bit of the memory word. So click on network 1 and say Control R, and then we will load the memory word, and we will load it with a 1. So we will set the first bit of it to true, and we will do it like this. We will use a set instruction, set, and we say M, which address is that? That's memory word 2, so we say M 2.0, and that will just create tag 1. And we want that to happen if something happens. We want it to be, what do we call it? product detection and tube detection. Okay. So if we have tube detection and not product detection, and then we use a positive, there will be work 1, then set the first bit of the memory word to 1, and then every time we index, we will shift that bit around. So now we have to actually okay, and then he wants to shift it 8 times. Then we actually have to say, okay, if M2.7, that would be the 8th bit of that memory word, that is true, go for positive 1, work 2, we want to, what do we want to do? We want to set the output, and the output was called eject. Okay. Do we need anything else? Eject. There's there. Well, that looks good for now. Let's try what we did here. Let's call the FB in the main OB1. Empty box. And we will say, what do we call it? Shift register? Shift. Alright. Call this one. It's a single instance. Name doesn't matter for now. And then it asks us for an output, of course. We'll just leave that empty because we don't really have a physical output. We just want to check if it works. So let's go for a simulation. Save the project, go on here, create a simulation. Load everything in there, and then if you click here on no action, it will actually give you a drop down menu, and we'll say start module, finish, and it will start the module here. Once it's running, you can like minimize that, and then let's see what we did here. Go and open shift register, and go on monitor. Now you see that we have our index like switching from true to false. That means like it's just because we don't have the real index wheel here. It's just like imitating a movement there, and so that's on. And then let's also create a watch table, watch and force tables here in your project tree. Add new watch table, and then let's say we want M2.0. Hit enter twice, and now just click on the address. Go on the right lower corner. It's kind of like an Excel table here, and just pull it down, and it will like open up. Like it will just like number it the right way. So now we actually have all the bits of the memory word 2 that we have here, and then let's go on monitor, and as we can see right now we have them all false. And let's open the shift register and go on the split screen here. So now we can see our memory word 2 here, all the single bits of it, and we can actually say, okay, we have tube detection. As you remember from here, it's tube detection is true and product detection is false. Then we will actually load the memory word, at least the first bit of it, and then it should shift through it. So let's go back onto the watch table and let's set the tube detection to true, and we will leave the product detection on false just to see what happens. So we double click on this one, say okay. Now it's set the bit there, and you see it will shift through. And then it will like just fall out because we have a tube detection, but we only have it on the positive edge. If I click that out, click it on again, it will start. Click it out, click it on again, it will start again. Now we have like 2 products that are not filled, and they wander through that memory word, and then once it's reaches the last position, it will just like reset. Why does it reset that? We go back into our network here. If we monitor this one here, let's switch that off. I'm sorry. Switch that off. Shift register. So what happens here? Indexing is clear, and then if we have a tube but we don't have a product, then it will set the bit to 1, and then it will like shift through here. Okay, and then once that is triggered, it will inject it. Well, let's check if that works too. If it even goes to 2.7, let's put that to set, download, and see if it actually goes through there. All right, so we go to shift register. We say we don't have a product, and then let's go back here and see if it comes through here. So it did. Let's put that back to a normal coil. And let's say we don't need the positive trigger here. We want it just to be on for however long that bit is on. All right, download it, load. Let's monitor what happens here. All right, shift register. Let's see what happens here. True, false, wanders through. Again, true, false. Oops. Wanders through. And then it jumps out. All right. So why is it that way? You might wonder, why is it not like shifting further? Because we didn't reset it. Well, I can tell you why. As weird as that looks here, okay, you have the address space 2.0 and it goes all the way through to 3.7, right? It's like everyone thinks like, yeah, it should wander through it, and then like 2.7, if we don't reset it, 3.0 all the way through 3.7, but that's not how it works. So the problem with that is that like we do shift left, and in a word, it's the same as in a byte. Like it wanders like, so if you put that on the side here, like if you would turn that 90 degrees in that direction here, this is actually how it would work. So like 2.0 starts on the right hand side, okay, and then it goes through. But also what happens is that in the other way around, like the address word has like 2 bytes in it, and it's also that it's a little bit different because the bytes are not like a like the word is not like a byte. So the word actually starts on the left side. So you have 2.0 through 2.7, and then the next one right on the right side to it would be 3.0 through 3.7. That is why it doesn't wander through, because 2.7 in this is like the last left bit that you have. So it's basically, if you want, so that it starts from the left hand side per byte, but it doesn't start per word. So you actually have like a word. Let's say this is two bytes here, okay? Just so this is 2 and this is 3. So you start here, so it wanders like this, and then it just ends here. If we would do it differently, and instead of like setting the bit 2.0 to true, and we would just move a 1 into the memory word, it would actually start here at 3.0 and then would go here through here, and then we would have to reset this, because 3.7 is not the last bit on the left side. After 3.7 there would be 2.0. I know that's kind of weird, and it's you actually have to think about that. If we can do the test here. If we go on the shift register, let's do it like this, shift register, and then we also go on the watch table, and then we go split screen. So now if I would modify this here to 1, see that 3.0 came on, and now it shifts through, and look what happens here. It goes all the way through 3.7, 2.0 goes through here, and then after 2.7 it will just fall down. 2.7, boom, gone. So keep that in mind if you work with shift register, that words and bytes are a little bit different structured, even though they come like from the address right behind each other, but it's actually reversed. So keep that in mind. That's really confusing, and that's probably why my user, like his name was Martin, that was so nice to send us the picture and the requirement. That was probably Martin's problem, because he didn't keep that in mind, that we have like the bytes and the bits reversed in a word. and that was probably the problem why it didn't work. If you actually want to use the option that you move a 1 into the word, then it starts here. You actually would have to reset the word by moving a 0 in it after you reach 3.7, or you move 100 into it. So if you go on modify operand, and you say 100, then it actually starts at 2.0. It's a little bit weird, I know that, but that's just the way those bytes and words are structured, and that's the only way to get around there. So I hope that helps, and I hope that actually concludes the shift register setup here. There's tons of other applications that you could use that for. There would also be other ways around this. You could actually just use counters, so every time you have a positive trigger of the index bit, you could just like count up, and once you reach 8 in a counter, you could just like reset the counter to 0, and also say, okay, if I'm greater or equal 8, reset counter to 0, move 0 into counter, and set the eject bit, and that would also do it. It's about the same amount of networks that you need and the same amount of code, so it doesn't really matter. To be honest, like in my career, I didn't use shift register so often, so it's really up to the programmer how you want to do it. As I said before, there's really no right or wrong to do something, as long as you reach your goal. The only thing that I can say is that you want to look at programming as like, even though there's no right or wrong, but there's a efficient and inefficient. You can really make a difference here by be very efficient by writing not that much code. That is really the only thing I want to give you on your way. So there's no right or wrong, but there's efficient, there's inefficient. And I said that before, I guess, but a really good programmer is really lazy. So you don't want to write too much code. So the lazier you are, the less code you write, the better of a programmer you are. So that being said, thanks for watching. And if you have tasks that you can't accomplish because you have a little bit of a problem with the code, just send me an email to m@themikepeters.com, and I will try to solve your problems. If it's not too big of a task, I'm not gonna sit down and like write 5-hour programs for you guys here. But if it's something simple like this, just shout out to me. Like I said, write me an email, m@themikepeters.com, and I will try to solve your problems here. Thank you very much. See you in the next video.